Here we go.
All right, we're there. All right. Okay, gentlemen. Hopefully this will all sail smoothly this time. And we're going to go to full screen, like better than what we had last time. Last time I was so involved in what I was doing, I didn't realize I didn't have full screen. Here we go. Edway, that's you guys. And then coming down here, by the way, this is still my favorite, under construction. It's always under construction. Okay, a glimpse at power supplies. Here we go. Now, first of all, here's what I want to do. My first opening point here is, lest you think power supplies is a simple and perhaps a dull subject, let's take a look at the outline. Well, the outline for power supplies can be quite involved. There's a lot of stuff there. I'd suggest you take a look at it and see if there's something in there that, oh yeah, I know this, I know that, I know this, I know that. All right. Okay, that's a good starter. By the way, there's other ones as well. Now, some of you guys are vacuum tube experts and some of you are transistor experts, but who knows? Then you got amplifiers, oscillators. And by the way, an oscillator is an amplifier with positive feedback. That's all there is to it. And then dB's easy wave. We've had that before. Oh, let's go on back here. Now, here's what we're going to look at. For those of us that actually were involved in designing and building power supplies in our early days, there are things that we had to look at and study. And of course, like everybody, we would build something simple. We'd find something that someone else had put up and posted it maybe on ARRL or on the web somewhere. And then actually web didn't exist at that time. And we look at that, and then don't forget the wattage. And by the way, with the linear power supply, and that's what we're going to be discussing most of the time tonight. We will, by the way, if we have time, get into some switching power supply characteristics. And there might be some surprises there for some people. And anyhow, transformers are rated in kVA rather than watts, just as a kind of a reminder. When you're dealing with rectifiers, you have to make sure that they're solid, that is, they'll carry the current, but also don't forget peak reverse voltage can destroy a rectifier. Okay, they need to have heat sinks to prevent damage. Yeah, they do blow up. Burn up is actually a better thing. Sometimes they can be quite noisy when they blow, by the way. Ask me how I know. To accomplish adequate filtering, well, we got to have different components in there. We got L-type filters, Pi-type filters, providing their RC. Maybe if they're RC instead of LC, they could still be L-type or Pi-type. And with capacitive input or choke input, we need to discuss what the difference is and why it's important to know on capacitive input power supply filters versus choke input power supply filters. All right. Reason why is because, to start with, a capacitive type filter requires or I should say, you're going to encounter a lot of surge current which can wipe things out. You can destroy a rectifier that is adequate for the amount of constant current, that is the average current, but not the inrush current. That can actually be really bad. Okay, now we're going to discuss the swinging choke tonight, which is something that maybe you guys know about and maybe not. We'll see. Then ripple. Well, we're all concerned about ripple because that's what makes, when you pick up your handy talkie or pick up the microphone for a bass unit, does it warble at you or does it have good audio like it should be? Another thing is, if you're going to build a power supply or you buy one, sometimes current limitation is very important. How do they do this? And we're going to look at just how that's done. Okay. You got a full wave rectifier that we'll talk about, bridge rectifier and how they're used, dual voltage systems. Then we'll maybe later, if we have time, talk about the switching power supply. Let's go in. Let's dive in. Okay, here we go. Now, by the way, these diagrams that I have and you guys can download are test questions that can be involved in this. I've used these diagrams for years. What's really good is I can pop this diagram into a test at the college, and I can ask 24 questions coming off of the same diagram. So I don't have to come up with a whole nother diagram just for a set of questions. I get like 20 different questions just for this diagram. All right, let's go in here. First of all, what's wrong with this circuit? Anybody? There's something missing on this circuit. There's no bleeder resistor here. There should be a bleeder resistor. Here's why. Charge this thing up and remove the load. And if you got the load off of here, whether it was removed while it was up or off and then you turned it up, that means that these terminals are hot. And as a result, this can be enough to be not only damage some equipment, but I'm going to tell you a true story after a while about a particular Navy chief got himself killed because he made a mistake. We're going to go into some of that. All right. This particular one here, if you have a bleeder resistor there, the whole purpose of the bleeder resistor is that whatever voltage is charged up on these caps has a load to go into, even if this load is removed. It might take, several seconds or maybe a couple of minutes to fully bleed this thing off. Bear in mind that this power supply can be a little dinky thing, but it also can be large enough to run a radar system, which is what I'm acquainted with. That's what I worked with when I was in the service. Okay, this is a half wave because there's only half of the time that the rectifier is working. However, the voltages here get up accordingly. Now, down here you have what's called a full wave center tap. And the full wave center tap then gives you your peaks twice per cycle. And so therefore, it's easier to rectify it and to filter it out. Now, notice I have question marks here. The reason why the question marks are there throughout the circuit is because I could ask, as I said before, legitimate test questions to my students. Now, this is a Zener diode. Some people call it Zener, some people call it Zener. Long time ago, I looked it up, and actually both pronunciations are correct, believe it or not. Anyhow, this is shunt regulation. Now, this one down here is series regulation. This one down here is shunt regulation. It's important to know the advantages and disadvantages of both shunt versus series versus shunt. Okay, so we'll leave it at that for the moment. We're going to come back to these though. I'm going to go through about 4 pages of this. And what I'll do is I will come back to one of these pages for some more questions. Now, what I want to point out here in this circuit, I have demonstrated in another page, so I'm going to leave it for now, but I want to come down here. What is this IC1? This IC1, if you were wanting, for instance, a 5-volt power supply, this would give you your 5 volts up here, but it might be 12 volts. Down here, you might want 5, or you might want a negative 12. That's what this guy is. Quite commonly, there is what they call a 7812 or a 7912. A 7812 is a positive voltage regulation. It's a 3-terminal device and very, very popular in a lot of circuits, and so it's well known. Now, this guy up here is a whole different story. Here's what's important. This resistor has nothing to do with that transistor. This resistor has to do with this Zener diode. This Zener diode in here is a reference diode. If this guy here was sitting at 5.6 volts as an example, that 5.6 volts provides a reference voltage at the base of this transistor. And if you recognize it, this transistor is in the common collector configuration, otherwise known as an emitter follower. Now, what I'm saying is that whatever this voltage is here at the base, the emitter will follow it very, very faithfully, but about a half a volt behind, in fact, more technically about 0.6 of a volt. So therefore, if this is sitting here at 5.6 volts positive, then that means that the emitter will be a half a volt or 0.6 of a volt away from that, sitting here at right on the button of 5 volts. What's really good about this is the output impedance of this configuration is very low, and a low output impedance is characteristic of a constant voltage source. So this eye here is very, very practical as a 5.6 volt here, therefore a 5 volt out, and this guy down here could be a negative, which would be a 7905. the 9 instead of an 8 means it's a negative output. You have to watch also the wiring of the pins, because the 7805 pins and the 7905 pins do not agree with each other. You have to be careful there. And you do have to have a heat sink on this unless you're only drawing a little bit of current, this being the variable load. I'll show you later. This guy here, by the way, has about 23 transistors, diodes, and resistors in here. It's deceiving. It's a little TO220 package, but it's got a lot of stuff in it that does a very tight regulation. And you won't have any ripple coming off of this guy. It'll be very, very clean. Now let's come down here to this one instead. This guy down here has an amplifier here, which compares the voltage of a reference voltage, whatever this might be, and it compares that voltage with this voltage here. So this circuit right here is simply a linear comparator. And what it does, it compares these two. By the way, this guy here is usually on a half a dozen transistors at least. You can make one out of any number of different components. But the whole point is that whatever this voltage is compared with this guy here tells this transistor to conduct more or less. Now, this is a shunt regulator. And as a shunt regulator, that means if this load suddenly goes more resistance, drawing less current, this guy here has to draw more current to make up for the change in current here. The advantage of a shunt regulation system is that the load from the power supply source over here is constant, because this guy here does a teeter-totter effect with the load. So if the load draws more, this guy draws less. If this guy here draws less current, this guy here has to draw more current, so that the current flowing through this circuit here is relatively constant. The advantage of a shunt regulation is a constant load on this source over here. That is not the way it is up here in a series regulation. In a series regulation, the current can change all over the place. That is the draw by the load. And this guy here just simply says, well, adjust the voltage for less current. That's all. However, if this guy here conducts more, he draws this point closer than to the source. Now, the advantage of this circuit is you can pop the load clear off. And this guy here will say, okay, but you still got 5 volts there. Load or no load, 5 volts. How much current? Well, that depends on what we need. But that's not true down here. Down here, you pull that load off, and if this transistor is not designed for that, this transistor here can say, oh me, oh my, this is more than you told me I was in this job for, and it'll pop that transistor because he has to take all the load because this guy here is gone. So this is the disadvantage of a shunt regulation system. The same thing would be true up here. That means up in here, you pull the load off of this guy, and that means that this poor Zener diode is now have to carry not only the little bit of load it had to begin with to compensate for changes, but now you pull this guy off, all of a sudden that Zener has to take all of the load. And you better have a resistor up here that's properly set for that to limit the amount of current where you're going to blow that Zener right out of the picture. So here's advantages and disadvantages of shunt regulation, series regulation, and shunt regulation. Now let's go up here. This is really an interesting circuit. Here is your 7812 that I described before. This 7812 here does a really good job, and it draws current through this resistor here and on out to the output, and it does a fantastic job. Like I said, this guy here has got about 27 transistors inside here, along with resistors, diodes, and everything else. But he's only good for about 750 milliamps. Since he's only good for about 750 milliamps, what happens if you get up there in the, say, 600, 700 milliamp range? The amount of current going through this resistor, this circuit is designed with certain values, and I'll point these out. The amount of current flowing through this guy here, let's say 600 mils, would be, look at where it is. This is the voltage between the emitter and guess what? The base. Forget this transistor here for a moment. If this voltage here gets to where it's about a half a volt and breaks over half a volt, goes up into 0.6 of a volt, guess what? This transistor here starts conducting because you have a bias voltage between the base and the emitter. And this bias voltage says to this guy, hey, get in here and help out. This is your power steering module, if you will. So this guy here conducts more. And this guy can be heavy enough to cover 3, 4, 5 amps. Well, this 7812 can't do that. But if you've got a good enough transistor up here to carry 3, 4, 5 amps, he'll kick right in here and add in. Now, this is still the guy that's controlling. Now, let's say that the current gets a little bit too much, and this guy here says, I can handle up to maybe 3, 4, 5 amps, but don't go pushing it beyond that. Let's say it tries to go higher. Well, if it tries to go higher, remember, we got current going through this guy. And this current flowing through here is negative to positive, and that's a PNP transistor like this guy up in here. Well, if this current going through this resistor gets to be more than a half a volt, this guy here starts conducting. He hasn't been conducting until now. So he only conducts if this voltage here gets a little bit higher than it should. And guess what he does? He shorts out this resistor. You short out that resistor, and this guy here says, okay, I quit, or he'll back off. So what is the purpose of this circuit right here? The whole purpose of this circuit is to prevent overcurrent. This resistor here, he's in there so that this guy kicks in and starts adding some power assist to this guy. So he's the one that's really controlling the regulation. So guess what you'll have? You'll have a really nice clean 7 or 12 volts come out here, and it's a positive 12 because this guy here is a 7812. So you see how this works in. So we have to understand how this thing works based on, guess what? The bias developed across this resistor here, which tells this transistor, we're getting a little bit too much current there. I'll tell this other guy to shut down. But until that guy, this guy here is transparent. He's in the dark. He doesn't care. As long as this voltage here is below a half a volt, he doesn't exist. However, this current here is what tells this guy to get in here and help out. So it's really a very, very nice circuit. And at first, when you look at it, it says, that's a little bit complicated. But after a while, you say, well, okay, that makes sense. Guess what? You could vary this, and you would vary, therefore, the amount of current limitation. In other words, if you wanted to limit this thing to 3 amps, never get up to 4 or 5 amps, what you would do is have more resistance here, because as the current goes through this guy, it builds up that base to emitter voltage and turns this guy on, which shuts this guy off. So, hey, there you go. That's current regulation. If you made this guy here variable, that tells this guy to start coming in either a little earlier or like, make this guy work for it. Comments or questions so far? All right, let's go to another one. Now that we're getting in here a little bit, we've got to have you something to chew on, right? All right, here's one similar to before. What's wrong with this circuit right here based on what I told you before? Surge current. Now remember something else. A capacitor is a dead short when you first turn this on. And usually we don't think of that. This capacitor, when you first build this and put it together, this guy here is a dead short. That means that this transformer running through this through this diode here is going to feed a whole lot of current to feed that capacitor. And as a result, you might blow this guy right out of the socket. So what? We come over here and we say, now that I know about that, guess what? That's why this resistor is in there. That resistor is in there to limit surge current. That's in there to limit surge current. That's what it's there for. It might only be a half an ohm. It might be 3, 4, 5 ohms. It might be a resistor fuse. If you've ever seen them, they look like a ordinary fuse, or maybe look like a ceramic resistor, but it's really a fuse. All right. Let's go over here. Now I've left out the surge resistor here, but there should be one. in reality, even if it's just a few ohms. This is a full wave rectifier system, all right? And because of the facing of the diodes, this is going to be a positive power supply. Now, down here, we have a whole nother story. This coil that's here serves a definite purpose. Surge currents with a coil says, not, you're not going to push that current through here. So what happens is a coil is an open circuit to begin with. So that by itself is not going to do much filtering, but we add this capacitor here. Now the two of them together work real well, whereas the coil simply resists surge values and helps the capacitor charge up. Now, one of the things that we learned a long time ago is if you're building a power supply for a transmitter, we found that this approach is better than this approach or even this approach, because this coil that's in here tends to smooth the current issues out under heavy current draw. So you'll find the people that build up their modulator circuits for power supplies, they followed this principle here because of the limitation of that surge current. Now, the most common power supply you'll ever find just sitting around will be the pi type. But here again, guess what? It's wise to put in, even though it's not shown here, it's wise to put in just a small resistance value to limit the surge current. All right, now, if we take this drawing here, well, wait a minute, I'm going to skip that one for a little while. I'm going to come back to it because I want to dive into this guy. See these arrows I've got drawn through here? This is a bridge rectifier used differently than this one. What happens here is if this is a 12 volt, 0 volt, 12 volt, and there was 12 volt in this secondary, 12 volt in this secondary, then what happens, you got a 24 volt transformer. Well, over here, you got a 24 volt transformer, but you got full wave rectification and come out with 12 volts. This guy here, if you got 24 volts here, you're going to have 24 volts over here. So the full wave rectifier will take the advantage of end to end without the center tap. Therefore, it's still full wave rectification. And what happens here is when this diode is conducting, so is this one. When this diode is conducting, so is this one. So there you go. Now, if it turns out that one of these diodes went away, you would find that showing up in the waveform. You'd find one waveform as a half wave, and then suddenly you'd find a missing peak. Now, here's the same circuit, but done differently. Now we're going to use a bridge rectifier, and we're going to use a center tap. And right away, that reminds us of this guy here, which is a full wave center tap system. And that's what this guy is. Now watch this. See these two diodes, this one right here and this one right here, they look exactly like these two with this ground, common ground here. So these two diodes here work like this circuit here. And these two diodes here work in the same way, but opposite polarity. That's the advantage of this circuit here. If you ever find a dual voltage output power supply where you got plus 12, minus 12 as an example, don't be surprised to find it's a full wave center tap using a bridge rectifier system. So there you go. What happens is these two diodes work together in concert as the reverse order of these two to give you a negative 12. Then, of course, you have a pi filter and a pi filter again. All right. Now, let's get into something that's a little bit tricky. This is an area that I happen to know that most, well, let me put it this way. Even if you do a fair amount of electronics, this is an area that is not familiar for most people. It's called a swinging choke. I haven't seen this in literature for years, but anyhow, I wanted to bring it in here because it's an area that I want to be able to discuss. This guy here is called a swinging choke, and over here is a smoothing choke. These chokes that are up here are actually smoothing chokes. They call this a smoothing choke to differentiate it from the swinging choke. All right, let's talk about this. This really gets into some very interesting area of physics, we'll call it. Particularly magnetics. Notice the arrow through that. The reason for the arrow through that is if you buy this transformer, you might see it's limited as the literature on it. Instead of saying, like, say, 15 henries as an example, it will say 5 to 25 or 5 to 15 henries. You say, wait a minute, is it 5 or 15? And the answer is, yep. How can it be both? What happens here is this is a very specially designed coil. Now, a coil has to have a core. Now, we're going to separate out of this. I'm going to bring up something else entirely different. Let's get down here to what's called variable inductance. All right, everybody knows about this when we're teaching somebody, except we usually put E up here, E over IR. E is actually short for electromotive force. And of course, we have amperes. By the way, 1 ampere is 1 coulomb per second, in case you want to know the more technical side of it. Then you have resistance. Now remember that there is such a thing as resistivity and conductivity. We went over that a couple of sessions ago. Conductivity measured in moles, and they're reciprocal from each other, right? But we call it resistance. But we're so used to talking about resistance, if I had 1 over GM, you'd say, well, what happened to my R? Well, that would be the reciprocal value, because the reciprocal of R is conductivity or conductance, measured in so many moles. And mho is the reciprocal of ohms. All right. Now, let's get interesting on this. First of all, in an air core coil, you run current through an air core coil, there is a magnetic effort. And here's something that most people are not acquainted with unless they've spent some time in some pretty good textbooks. First of all, there is another one over here called Magdala Multiforce, which is the same as EMF, except this is magnetizing. This is an ampere effort, that is a magnetic effort, depending on how many amps and how many turns of wire. Now that's important. If you have 2 amps and somebody says, okay, that's nice, but how many turns? Because the magnetic effort that's there, called magneto-motive force, depends on how many amps and how many turns. Now, this is an effort. Think of it like voltage is an effort. Now, just because I got 12 volts, that doesn't mean I'm going to have 15 amps. You have to have, depending on the amount of resistance. Well, down here, how much flux there is, and that's the Greek letter phi. I wanted to put in the lowercase, which is really more proper. But anyhow, that's a Greek letter phi, which stands for flux density. Now, this up in here, there's an effort to create flux. It's like voltage. There's so many volts, but down here, there's so much effort, magnetic effort. Now, depending on how much reluctance there is, you'll have a certain amount of flux density. And that's the way to describe it. By the way, one time when I gave a presentation on this, which won't give into details, but it was for a bunch of, I was an instructor at Boeing, and we were asked to give a class for a bunch of engineering and engineering aids on magnetic amplifiers. And so we got into this pretty deep. Now, what I'm saying back here is, if you have an air core coil and you run 3 amps through that coil, you will have a certain amount of magnetic effort. So how much flux is there? Well, if it's an air core, it has a permeability of 1. You say, wait a minute, what's permeability? Permeability is the ease by which we set up a magnetic field, okay? Ease. Air has a permeability of about 1. Technically, the 1 is a vacuum, not air. So air has just a tiny smidgen bit more permeability than a vacuum does. So they just roughly say, it's 1, leave it at that. However, iron, if you put an iron slug in here, iron has a permeability, or if you will here, of about 2,000 times more than air. Therefore, and we know this just for application, if you put an iron slug in here, all of a sudden that coil has a lot more magnetic flux. You haven't changed the effort. You have not changed the effort. But you put a slug in here, and now you've got 2,000 times the number of flux lines. And depending on what book you read, they might be measured in Gauss, Webers, or Maxwell's, and who knows whatever. If you read a book, be careful. I went through about 8 college textbooks one time looking at all this just to see what the professor said. Some of these professors would jump from what they call the MKS system to the CGS system without warning. And the poor guy who's trying to learn, it can be confusing. So if you do go into this with any college textbook, be careful, because I have seen this myself, and it can be confusing to say the least. But let's go back to this. If you have a slug that you run up and down, guess what? That's how they used to tune a lot of the old time radios. In other words, if you've got a super head-to-down receiver and somebody tells you, okay, what's the frequency for the IF? And they say, well, in a typical, 5-band radio, for home radio, it's 455 kc. So you tune the IF strip for 455. Now, if you go to an FM, it happened to be 10 megacycles instead of kilocycles. Well, when I was working with radars, we had very high frequency up in the gigahertz coming down into an IF strip, and the IF frequency there, and by the way, this was all tubes, transistor did not exist yet. The IF strip there was a whole different frequency. It didn't follow the 5-tube superhet principle. Let's go back to this and just do a review here. Magnetomotive force is the effort to create a magnetic field. It depends on how much reluctance is in the field. Iron has a lot more permeable or less reluctance, and therefore you drop iron into that and you get a whole lot more flux. This is what allows us to tune a circuit with a variable slug. So what you're really doing is moving that slug up and down, okay? Now, here's something that's not well known. All of that so we could come up with this principle. This iron core, if you have a choke for a power supply, you want something that's got a fair amount of inductance measured in henries. Now, what happens is, if you design this core a very peculiar, I'll say peculiar or particular way, as you shove more and more current through it, the inductance saturates and therefore falls off. What would happen if this core was saturated? Guess what? It would start behaving more like an air core. So as you pull a slug out of this, it becomes more like an air core, right? Well, as it turns out, there are certain chokes that behave in a rather peculiar way, and it's based on how they do the laminations for this coil. And this thing here will saturate following a curve. I wanted to show some curves on this, but I just couldn't come up with them. It actually goes up, and the curve goes up and then flattens out. And as the curve flattens out, what it really says, this may be starting at 25 henries, but as you have more and more current through here, it starts approaching saturation. And as it approaches saturation, it drops down to only 5 henries. That's really an important consideration, and I'll tell you why that's so important. This is not only true for coils, there are some special transformers that most people never stop to think about, and they may be in your computer. Let's go back. Going back here to where we were a minute ago, this guy here is what we're talking about. As you have less current, you may have 25 henries. But as you finally wind up with more and more current going through, and remember, on the very slope of the current, this guy here can diminish and become only 5 henries. However, this circuit over here, whatever henries you got here, if that's 15 henries, it's going to be 15 henries all the way. Will it ever saturate? All coils can saturate, all of them can, but this guy here is especially designed. The laminations is what's designed into this, and the laminations are designed with air gaps. And with those particular air gaps in a certain way, the core will saturate or begin to saturate, therefore changing the inductance from 25 henries or 15, let's say 15, and as it begins to saturate, it'll drop down to as low as 5 henries. That's what they call a swinging choke. Now I'm going to show you something that was an offshoot of this as well. Down here is an ordinary transformer, except it's not an ordinary transformer. This transformer here has a technical name called a Saturable Reactor. The Saturable Reactor, by the way, is a common thing for, in fact, I have one. Common thing for missionaries when they go over to third world countries, because the line voltage over there is notorious for swinging all over the place. Let's say you have some equipment, you paid some good money for it, and you want to be able to use it on the mission field, and the voltage has a wild swing, and the first thing you know, your equipment is smoking. Now take this diode out and take this capacitor out, so this becomes just an ordinary transformer. This might be 110 volts in, 110 volts out. But what this guy here is designed for, following this principle that we were talking about up in here, this guy here is designed so when the line voltage gets up to around 95 volts, anything beyond 95 volts begins to taper off. You got full voltage, 110 coming off of this, even when this is 95 volts. So in other words, you have a few more turns here, because your turns ratio is just a smidgen here. So this is a little higher turn. So you have 95 volts here, you'd have 115 volts coming out here. Now, here's what's interesting. Since this guy here will saturate with higher currents or higher voltages, if you will, then that means that as the voltage here goes from 95 volts up to 150 volts, up to 175 volts, guess what this is? 115 volts. So these guys here were a real favorite among a lot of missionaries. I have one that's about the size of a loaf of bread that you buy off the store, and it weighs about 35 pounds. It's heavy. And by the way, they get warm. And when the people first use them, they should get that warm. And I said, that's commonplace. They do indeed get quite warm. You say, okay, fine. I'm not on the mission field. I have no use for this. And the answer is, wait a minute. Back in the early days of computers, before the ones that we're using right now, when the S100 systems were around, they all used, at that time, they used TTL circuits. TTL circuits are critical for voltage. You go below 4.5 volts, they don't work right. You go above 5.5 volts, they don't work right. You want 5 volts. And so what happens is you set up a power supply system with all the regulators and such as that to give you nice 5 volts. Now let's say that the line voltage, you are out at the end of a country road or somewhere, and you're at the end of a line. Your line voltage is not going to be what you'd like it to be. So what happens is there was a lot of problems that people were starting to have with the S100 systems back in the early days. And these are, early computers before anything like we're using now. So what they did is they said, oh, well, we know a principle that was used here a long time ago. So what they do is they come in with a power supply that's called a brown-out power supply. People bought these. They knew what they did, but they didn't know how they worked, and they couldn't care less. In other words, they said, hey, a brown-out power supply, I put that in, I will have a nice constant voltage, and I'm happy. So therefore, I'm willing to pay extra money for a brown-out power supply. And that's what they're known as. If you want to go out on the web and look them up, you'll find they're listed as brown-out power supplies. What they are is a, shall we say, a new version of this transformer right here. They are, in fact, a Saturable Reactor transformer. I dare say, about 19 out of 20 people that bought brown-out power supplies had no clue on how they worked, only the fact that they did work, and that's what helped them. That's what the really planned on, and they were glad to pay the extra dollars just to have a good, dependable voltage output of that power supply. With line fluctuations, didn't bother them. So this was a real big thing. If you were building computer systems like I was, we actually built custom computers for law enforcement and a lot of places. In fact, I installed, built and installed the very first parking ramp computer in Minneapolis, Minnesota, back in the days when these were all fairly new. Any questions? This is kind of confusing, but understand it's when the core saturates, and it takes a special design in the laminations. Looking for questions. Don't see any. All right, let's go back to something else. Here's something that some of you, the older guys in the group would be interested in. Back in the days of the 50s, when you had a radio in your console and you turned it on, you would hear a hum in the dash. That's because there was a coil, that is a device in there. It looked like a large capacitor, but it was a 4-pronged device. And what it was is a vibrator. Well, your radio requires, let's say, about 250 volts, tubes. And you got 6 volts. You know, this is before 12. 6-volt batteries, 6-volt radio, and this thing in here just a humming away. What it really was this. It had contact and break contact, back and forth in here. As soon as you turn it on, what happened is you can't get DC through a transformer. You'll burn up the transformer. However, this guy here would buzz back and forth, make and break contact, and guess what you've got? Pulsating DC going through the primary, which shows up in the secondary as your 250 volts. Then you run it through the typical filter situations, and your vacuum tubes are nice and happy. And of course, you had to be careful because your tubes were 6-volt filaments, and people that took a 6-volt radio out of their old car and put it into a 12-volt car wondered how come it didn't work anymore. And these guys, you could actually hear them. Okay, if you want to do lab work, and some of you would like to play around labs, and some of you could care less, but let's do this. A chip here, a very favorite chip for a lot of experiments, called a 555. Now, the 555 could be run in a monostable, but it's typically astable, which means that when you turn it on, it's got a square wave output. You can take this and vary the frequency of this in through the primary of this transformer, and because it's pulsating, what happens is it acts like AC, and over here on this side, you'll have, guess what? AC. Now, what's really interesting, this is typically, let's say, a 9-volt supply. These things like voltages anywhere from 5 volts to 9 volts, no problem. And as they come in with that particular voltage, if you vary the frequency, an interesting thing happens. If you vary the frequency, you'll find that the voltage changes. I call this a squeaker circuit. So if you vary the frequency, then you'll find that the voltage over here will change. And as you go to a higher frequency, the voltage up here will increase. Okay. By the way, here's those two 3-terminal regulators. They're TO220 package is what they are. And here I show them again at 7805 and 7812. So they're positive regulators. This is an interesting thing to put on a breadboard and play with. I think you find it interesting. All right, let's go over here to this circuit here. This circuit here, I built this, my first power supply I ever built, I was still in the Navy at the time, everything was vacuum tubes. And so I built equivalent to this circuit right here. Now there's an important feature here I want to point out. First of all, the Zener Diode here is like the tie bar on your car between the left wheel and the right wheel. So if this moves up here an inch, this one here moves an inch. Well, let's talk about volts instead. Let's say, for instance, that this guy here, first of all, this is a 9-volt Zener, and this resistance right here is picked to get this in the linear portion of that Zener. the idea is that if this voltage here changes and goes up 20 millivolts, well, guess what? That'll come up here, 20 millivolts. And as this goes up 20 millivolts, it will make this transistor, which is an NPN transistor, it'll make it conduct more. Well, more current flowing through that resistor there causes this guy here to conduct less. Because when you're coming off of the collector of one into the other, this acts as an inverter. However, this guy here is not an inverter. As he conducts less, he has less base current, which tells this guy here to not bring this line as close to the power source. So what happened is when the voltage up here starts to increase, and we don't want it to, this comes down through here and says conduct more, conduct less, making this voltage fall back down to where it's supposed to be. So this is a really good tight regulation system. Now, the reason why this guy down here is a variable resistor is because it allows us to tweak this just a little bit. Let's say, for instance, we have an output that is 12 volts, but we want 12, but it turns out is, well, it's 12.3. Well, then we can adjust this right here to trim this down to bring it exactly down to where we want it. This is a very tight regulation system. Now, in this particular one, what happens if this Zener diode is pulled out of the circuit? If this Zener diode here is pulled out of the circuit, then this guy here stops conducting, which makes this guy conduct more, which makes this guy conduct more, and this voltage here could go soaring up to, say, 25 volts. Now, the one that I built when I was selling the service was all tubes, but it was on the same principle as this. And for voltage reference, it used a tube called an OC2, which was a VR105. It had 105 volts across it, and it glowed. You know, like we used to say in the old days, real hams work with tubes that glow in the dark, right? Okay, I had built this to power a ARC5 receiver. Sometime that'll be a good discussion for a little bit of antiquity, if you will, because some of the old radios that we used to buy war surplus and then use as real stuff. Anyhow, I had this power supply sitting up on a cabinet, and my 2-year-old son came along and found some switches. Well, he knows how to flip switches, so he did. And when he turned it on, except it was all tubes now, it came out with 250 volts DC for the ARC5 receiver, which worked real good. The only thing is, this guy here was a VR tube, which glowed, oh, real pretty color. So he looks up there and he sees this pretty glowing tube. So he pulled it. And when he pulled it, it stopped glowing. Well, disappointed, he just laid it down, walked away. Well, sometime later, my wife happened to hear this kabowie in the other room. She went running in there to find out what was going on. 2-year-old son, he's long gone, but no, well, she could see it was turned on, but she couldn't see any smoke. By the way, I took it apart later and I found that a capacitor had given up the ghost and it shredded its innards all over the inside of that ARC5. What happened was it was this guy right here. When he pulled this, the voltage regulation went to pot, and instead of 250 volts, it went up to 425 volts. And the ARC5 says, this is more than I want. So therefore, it blew its cork. All right, enough of that. Let's go down here to this guy. This guy here is obviously another picture of shunt regulation. In this case here, this shunt diode here, I should say this Zener diode here, comes over and controls this transistor, which controls this one, which controls this one. And here again, if you pull the load, that means this guy here has got to take up the slack. So the way that these guys properly work is to take up the variance over here, but not the full load. All right. This is not a good thing to have for heavy loads, because you don't want heavy load pulled in this guy here to take all of that. Okay. All right. So far, we're good. All right. Let's see. Let's go on to something else here. By the way, I'm going to sidestep just a little bit. We had a power supply that was built along, let's say, this principle here, and it was for a radar This was a fire control radar, so it had a dish that would point at an incoming target, and from that you would determine how far away the target was, what direction they're moving, and therefore how to compute where to put a 5-inch shell out there to wipe out the target. So obviously that power supply was pretty good size. It was a Herky thing. I mean, you're talking about lots of current, lots of voltage. What happened is this coil was shorted to the frame of the power supply. And because it was shorted to the frame, here's what happened. The techs on board the ship were trying to find out why this power supply kept throwing the breaker. And they couldn't figure it out. Finally, a chief, a fire control chief, who should have known better, he pulled the power supply out and put it on a rubber mat. Now remember, ships are made of steel all over the place, but this was a rubber mat. He put it on the rubber mat, but he did not put a grounding strap between it and the frame. That's mistake number one. Mistake number two is he leaned over and his leg made contact with this unit that was sitting on the rubber mat, and he reached over and grabbed a hold of a chrome-plated handle to steady himself while he turned on the power. He became the grounding strap, and he paid for it with his life. All I'm saying is power supplies may look simple, but if you get into some big stuff, like if you're running a linear and you got a power supply to run a linear and it's all homebrew, you know, you're into dangerous stuff there, and you got to take every precaution. Now, when we're working with low voltage, we tend to be a little bit careless, you know, transistors and such. But those of us that came through tubes are a lot more cautious. The control amplifier that I worked at on board ship, I was on the repair ship, ran on 800 volts. And that particular power supply or amplifier, what it did is it controlled the amplidyne that controlled the gun mounts. And you could make those gun mounts so fast that if you were in the gun tub in an area called dead man zone, you could not move fast enough. And so those things would really move, and they had to accelerate fast. And then the adjustments I made was to bring the gun on target and not sit there and quiver, rattle, or shake and such and oscillate, but just settle in on target and then follow the target very closely. So we're talking about some serious stuff there. Okay, we've gone through basically everything. Let's touch on just one thing. And this is an area that you could spend a lot of time on. So all I'm going to do is just kind of breach through a little bit of it. A switching power supply, like what you'll find in your computer, not a linear power supply. This is a switching power supply, has a whole nother set of characteristics. It's actually two power supplies. The circuit that I have shown here will vary with every manufacturer because you've got copyright, patents, etc. So here we go. First of all, you have a basic power supply in the front end of this. All it does is take the line voltage. And by the way, you'll notice this unusual aspect here. This is called a hash filter. The reason why it's called a hash filter is because these things make a lot of noise. What happens is you don't want this noise passed through and getting up into the power line, and all throughout your house, you have all this horrible hash in there because of your power supply for your ham rig. And it shows up in everything. Well, what happens is this is a special hash filter, not just simply rectification filter, but a hash filter to keep this from getting out on the line. Now, what this does, this supplies the power voltage for you to work with. Now, first of all, AC is not meant to go through a transformer, and you don't want it going through the primary. So what you do is you have this guy, which is open. Now remember, the technique here changes. All I'm doing is giving you some basic principles. If you find this voltage up here, sitting up here, by the way, about 162 volts, and this guy here is caused to snap, that pulse I got there, that means that this guy here becomes a very powerful conductor, and he causes a pulse of current then to go through this primary. And notice it matches the polarity of this transistor. Therefore, this guy here will be a pretty herky transistor in your power supply. And what he does when he snaps that, that means that you have a pulse over here on this side. Well, let's say, for instance, you snap it, snap it, snap it, and this guy here, an oscillator pulsar, tells it to hit this, oh, let's say 400, 500, 600 times, maybe 3,000 times a second. What will happen then is you'll have a frequency of pulses coming through here, which are simply rectified and filtered, and out you go. Now, there's two principles here that are not, shall we say, often overlooked, not realized. One, I want you to look at this circuit here. This is an interesting circuit. First time I ever saw this, I thought, oh, come on now, that's a joke. You got to be kidding. Where's my April Fool's stamp? This is a SCR. There's a circuit over here, which is a trigger circuit. And if this trigger circuit ever fires, that is, it gets to a particular voltage, and there's a Zener there, if that ever triggers, that means this guy here becomes a dead short. And as a dead short, we're hoping to blow the fuse. The whole reason for doing this is if the voltage gets too high, we don't want to damage our equipment over here. So this SCR, a crowbar is what it's called, and it really serves the purpose. It's in there to protect your circuits over here. It is not in here to protect the power supply. It is in here to put a drastic load on this, and this guy here says, whoa, wrong, blow the fuse. That's what it's there for. Now, to isolate this circuit here from this circuit here, we have to have isolation, yet somehow pass a signal. Well, in this particular illustration, what we have is a LED and a phototransistor. The idea being, see, this resistance in here determines how much this will glow. The point is that when the voltage up here gets up to the voltage we want, because this fire here is just firing away, bang, 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 bang. What this does, this is feedback back to the oscillator and telling the oscillator, don't go any higher, don't go any faster. So it starts off pumping this guy up. It's like a air compressor, if you will, pumping this guy up primary to secondary. And when the voltage gets up to where we want it to be, the LED says passing on with optically passing on. So it's an opto coupler and yet an opto isolator passing on to the oscillator pulsar circuit, and it says, hey, back off, hold it right there, don't go any faster, and therefore it can cause this guy here to increase frequency or decrease frequency. All right. One last comment. If you ever take a look at these, you'll find that this transformer here is not a big, heavy transformer. And you wonder, what on earth is going on? There's a company in Seattle by the name of Lambda Corporation, if I have my remembrance set in correctly. They got to thinking about something. When they discovered that the higher the frequency, the smaller the transformer. Big 60 hertz, 50 hertz transformers are big and heavy. That's what your linear power supplies have. However, there's a 400 hertz transformer that was used in the military in Second World War on the airplanes. Why 400 hertz? Because it did not have to be a big, herky transformer. They used these transformers because that way the airplane did not carry a lot of excessive weight, trying to cut weight down as much as possible. So the guys at Lambda Corporation discovered that they could get a whole bunch of these really cheap. So what they did is they designed their circuits along in this method here. And when they designed these circuits, they made them as switching power supplies, and they sold like hotcakes. And they, to the best of my knowledge, were the first ones in industry to develop this particular idea and put it out. And they built the first power supplies that were switching power supplies. Now that's what you expect, like in computer systems. Well, that is to a close, but let me draw off one last thing here. If you ever want to, a lot of you guys have the Astron power supply. I'll just touch on this real quick so you can come back to it. In the Astron power supply, they have this particular circuit. And what I've done, I took this particular circuit and made a copy of it, and then I highlighted certain areas of it in order to illustrate how this thing works. And to show you that, those schematics are available. You just bring down to this one here as an example. This one here is the same circuit, but this time what I'm doing is I'm showing the main current path. This is using a full wave. But by the way, notice that there are two center tap full wave rectifier systems here. One of them is for this control circuit down here, and one of them is up here following through with all of this, shall we say, feeding out for your transmitters, transceivers, whatever. Let's go back now. Now let's look at this one here. The same schematic, but this time what I've done is highlighted the control circuit. And then if you go back, you can look into the protection circuits. It's in there. There's 3 or 4 different protection circuits. And by the way, guess what? There's your crowbar. Now, this particular chip that's in here is the key to this whole thing. And let's take just a quick moment without going through what those are. Let's drop down here and show you what this chip is. Usually it's in this form here in this particular package. Let's go down and take a look. Oh, they've got all kinds of applications. By the way, those of us that designed and built power supplies, whether it be for real or be it for just play and toying with, this was a favorite chip among all the people that I know of that worked with these different power supplies. This guy here was really good. And he could control anywhere from 7 volts to, I don't know, on up to the voltage. I forget now. It's been too rusty. All right, one last thing to show you. Come down here. There's more applications. There's more of them there, more of them here, more of them. A lot of good stuff to go by right there. And there, more, bunch of them. This is what I want to go. This is what's inside that chip. One chip has all of this in here. That chip can be used for voltage control, current limitation. It has a considerable amount of use. And this is a well worth thing to follow through on. So I put it in there so that you guys can chase through it if you want. And with that, I'm all done. I'll turn it back over to you, Ed.
Oh, thank you, Dave. I have one quick question for you.
Sure.
You got my interest with the permeability of the transformer core or the slug. Does that change? Is that a constant or does that change with frequency?
Constant.
It is a constant.
Yeah. And what happens is Collins, by the way, made a receiver called the 390, and it was magnetically tuned. When you turn the tuning dial, it moves slugs up and down. Instead of tuning with the capacitor, it actually moves slugs up and down. It was linear tubing.
Fascinating.
The iron, well, first, there's one other thing. At the higher frequencies, maybe I'll take a different approach to your question. In the slugs, those were not solid iron. They were a powdered iron in a some kind of a, like epoxy as an example. Right. The reason for that is because as you go up in frequencies, the core starts absorbing too much. And so what happens is in transformers, they always had laminations to reduce the eddy currents. And the eddy currents at radio frequencies could not be tolerated. So what they did is they went to powdered iron, and then that was moved up or down for tuning. And that was because of the frequency. The cores at higher frequencies, there was eddy currents that started being a real problem.
And that's a current on the outside of the core?
The core itself would actually produce eddy currents, yeah. And so they had to go, like the higher priced transformers were thinner than the other ones, and they're actually glued together like with shellac and such. Okay. And but as you go up into higher frequencies, they couldn't use iron laminations And it had to be soft iron because soft iron does not retain a magnetic field. They had to be careful of that.
Gotcha.
Residual. Steel would have residual, but powdered iron or soft iron would not retain any magnetic field as a residual. That whole area is intentionally interesting.
Yeah, really, the science of it is fascinating. Well, thank you, Dave. Wow, you have such a way of presentation. That's pretty amazing.
Well, hopefully I didn't confuse the issue.
That's what the video is for. We can rewatch and dig back into certain points. I really appreciate it.
Well, I had to put my thinking cap on.
Thinking cap.
Because that's an area that I haven't dealt with for 20 years.
Wow. That's so great. Fantastic. Anybody else have questions for Dave before we shut down our net?
Yeah, one. I don't know how to. Wait a minute. I don't know how to. Can you guys hear me?
Yeah, we got you, Frank.
Oh, we did. Oh, okay. I didn't. Yeah. No lights came on or anything. I didn't know. Anyway, yeah, Dave. I was wondering. From yesteryear, something hit my head. Back EMF, and on large core iron transformers and stuff like that. They had a deal where you could buy these transformers that were screwed together and had the laminates and everything else, and you could lighten them up if you had lighter loads and everything else. But if you did, so too much and didn't change something, and I forget what that was, you didn't have enough back EMF and heat buildup. And so exactly what is back EMF and how does it keep the transformer cool?
Well, actually, anytime there's a very complex situation on what they call the resistance of the core, and it's depending on frequency. But what you're talking about is counter EMF. Any magnetic field that collapses will cause a back EMF, which can destroy complex. Now, in terms of heating up the core, I'm not following that concept, but I do know that you go up in higher frequencies and also heavier loads, the core will get hot. And when you get into some of this, you have to consider what they call the efficiency. A good transformer is not 100% efficient. None of them are. They might be 92%, or it might be 98%. And a lot of it had to do with not just the core windings, but it had to do with the magnetic coupling, the method of coupling from primary to secondary. So there was a lot of design considerations, and I'm not calling myself a designer, but I know about it. There's a lot of design considerations on proper coupling between primary and secondary, and the type of laminations, because those laminations can get really hot.
Okay.
I don't know if that answers your question, but I haven't heard of how to lighten it except for frequency and the way they're built. All transformers get quite warm.
Okay, thank you.
Yeah. It's the best I can come up with right now.
That'll do.
Well, I do know this, that the whole field of transformer design is a lot more involved than I can get into. I know enough about it in terms of frequency consideration and the magnetic constraints. And they also have, like I said, they've got flux coupling. Oh, here's something I'm going to throw in entirely off of what we're talking about. But when you are adjusting or setting up, for instance, a IF strip in a radio and you're tuning it, if you get into overcoupling, this is too much coupling between primary and secondary, it will not give you the proper curve that you want for bandpass considerations. So you can actually get into overcoupling, and that's bad. Unless you intentionally want it. I've never known of anyone that wanted that.
Didn't they call it an oscillator?
No. Yeah. Oh my. Heterodyning is an interesting thing. Ed, something that if later down the line, there is a schematic that perhaps not too many people know about. You know, everyone knows about the VFO and the BP. You know, the VFO and the BFO, but what about an LMO, linear master oscillator? All of your new equipment have that. In other words, if you buy a new Kenwood, a new anything at all that has that tuning, it's an LMO, linear master oscillator. And it's a rather interesting facet in the schematics to cover sometime. And it doesn't have to be me by any means.
It's on my list. All right. Anybody else? Questions for Dave? Nobody wants to know his favorite color. All right. Thank you, Dave. Amazing. I'm going to go ahead and stop the record.